Good morning, everyone, and thank you for joining us today. My name is Madison Deal, and I'm with AIST, and I would like to welcome you all to today's webinar, which is the second in a three-part series on hydrogen, hydrogen production, applications, and challenges. So our goal for this webinar is to follow up on the first webinar that we had in 2023, which discussed hydrogen colors and types, as well as injection into the blast furnace. This second webinar looks at the general production, applications, and challenges of hydrogen in steelmaking processes before we have a third webinar that will take place in April, on April 2nd. And this is going to be focused on hydrogen-based DRI production and SSAB's hybrid pilot plant results. So please be on the lookout for that link when it becomes available. I'd also like to take a moment to recognize the Decarbonization Subcommittee, our chair, Felix Furstbach, and our webinar chair, Joe Mori, for all of their support and work into putting these webinars together. And would also like to recognize today's sponsor, Big River Steel. Thank you so much for supporting today's webinar and for being such a great support to AIST in general. So for our antitrust guidelines, this is a technical presentation that's focused on knowledge sharing. So please no discussions or questions relating to pricing or competitively sensitive information. And our anti-harassment policy, AIST is focused on keeping this a safe and harassment-free environment for both this webinar and all of our events. Couple guidelines for the webinar itself. So your audio as attendees has been disabled, but please submit all your questions via the Q&A function in Zoom. That's likely in the bottom of your screen or located in the More section. So as your questions come in, we will be holding them for a Q&A section at the end, or they may be answered via the chat. So please ask any questions that you'd like throughout the presentations. This presentation is being recorded along with all of our other webinars. It will be available on AIST's website, so no need to record on your own. And if there's any technical difficulties, please email training@aist.org. And now, without further ado, I'd like to introduce today's moderators. First, we have Mike Grant, who is an independent consultant with 40 years of experience in the EAF and iron-making technologies, and David Marshall, founder of Performance Improvement Incorporated and the founder of the Decarbonization Subcommittee. Take it away, guys.
Thank you, Madison. On behalf of Mike and myself, again, we welcome you all to this second hydrogen webinar. We have two presenters, both with great topics. The first is Ian Sutherland. Ian's the founder of System Zero Consulting, which is guiding organizations through industrial decarbonization, and hydrogen integration. He turns net zero strategies into actionable results through systems levels thinking and rigorous economic modeling. Ian, please take it away.
I think you're going to introduce Megan as well.
Yes. Megan is a process engineer at Hatch. She specializes in hydrogen systems and in decarbonization processes. She supports large-scale projects that enable sustainable energy and emissions reduction.
Before Ian begins his presentation, you'll also see a little pop-up on your screen. So we're going to release a poll to the group to kind of pick your brains on what your thoughts are on hydrogen. So that'll be available for you to answer throughout the presentations. All right, Ian, all yours.
Fantastic. I hope everyone can see my screen.
Yes.
Move the poll out the way. Okay, thanks for the introduction. This is a huge topic, and it's going to be difficult to cover it comprehensively within the time we have available today. So please take my presentation really as an introduction to the key themes within the topic. So this is the structure of the presentation, which has 6 parts. And I would just like to let everyone know, if they would like a copy of the presentation afterwards, then please send me an email and I'll send it to you. And my email address is on the last slide of the presentation. And as was mentioned, I hope we do have some time left over at the end in which we can cover some of the points in more detail. So firstly, to the introduction section. I guess the first question is, really, why are we interested in talking about hydrogen? And the answer to that is that hydrogen has some unique chemical properties that gives it the potential to significantly reduce carbon dioxide emissions from both iron and steel making. However, for hydrogen to fully contribute to the decarbonization of iron and steel making, the process of producing the hydrogen must also have zero or low carbon dioxide emissions. And this means that there are two perspectives to take when looking at the topic of hydrogen in iron and steel making. Firstly, there is the use of hydrogen in the processes of iron and steel making. And then secondly, we need to cover the options for producing clean hydrogen. But first, if we are going to explore the use of hydrogen in iron and steel making, then we really need to understand hydrogen from a chemistry perspective. I'm sure many of you already know about hydrogen, either from your work or if you remember from school science lessons, but I just want to set out a few key facts about it. Firstly, in atmospheric conditions, hydrogen is a colorless and odorless gas. And secondly, it is the lightest element and it is the smallest molecular gas. And what this means is that it makes it prone to leakage and diffusion through materials. And then thirdly, hydrogen generally only exists in the environment in the form of a molecule such as water, H2O, or methane, CH4. And there is also a contrast in the definition of the amount of energy that hydrogen contains. Because on the one hand, when you look at hydrogen's energy density by mass, that is joules per kilogram, it is vastly superior to other fuels. However, on the other hand, when you look at its energy density by volume, it is significantly inferior to other fuels. And this point is important because when we are considering hydrogen consumption and transportation, we are generally more interested in energy density by volume than energy density by mass. Although there is emerging potential to extract pure hydrogen from deep geological deposits, and you may have heard about discoveries of natural hydrogen in France and in Canada, I think. The only commercially available hydrogen production pathways that are available today either involve splitting water into hydrogen and oxygen, or splitting methane, natural gas, into hydrogen and carbon. So this now brings us to the pathways for using hydrogen in iron and steel making. And there are two. Firstly, hydrogen can be used as a chemical reactant in various reduction processes. And then secondly, hydrogen can be used to replace coal, coke, natural gas as a source of thermal energy. So firstly, considering hydrogen as a chemical reactant, hydrogen is a highly effective reducing agent. And this is because it has a strong affinity for oxygen. And what this does is it allows it to convert iron oxides to metallic iron while only forming water as an output. Also, because it is such a light, fast diffusing gas, it can penetrate into porous iron ore much more readily than carbon-based reactants. And this leads to rapid and uniform reduction. And so this combination of favorable thermodynamics, fast kinetics, and clean reaction products makes hydrogen attractive as a chemical reactant for low carbon iron making. And then hydrogen's combustion properties. Hydrogen can also be burnt to generate thermal energy, just like natural gas or coal. But the difference is that the process of combusting hydrogen produces only water rather than carbon dioxide and water. And there are other positive differences, such as a faster flame speed, but also there are some negative differences, such as higher NOx emissions, elevated moisture levels, and different flame behavior. So in summary, over this part, I just want to recap that hydrogen has the potential to enable the decarbonisation of iron and steel making as both a zero carbon reactant and a clean high temperature fuel. As a reactant, it can replace carbon dioxide emissions with water. And as a fuel, hydrogen burns carbon free, but its integration into production systems must also address NOx, moisture, and flame behavior. However, its climate benefit depends on having access to low carbon hydrogen. The hydrogen production pathway matters as much as the end use. In this second part, I'm going to very briefly describe where hydrogen can be used in the processes of iron and steel making. And for each process, I will provide some real world examples. But this section is only intended to be an overview. And as Medicine's mentioned, there have been previous AIST webinars that go into more detail on this. And there's the future planned webinars as well on this topic. In addition, and interestingly, for anyone that is planning to attend the AIST Tech conference in Pittsburgh in May, I've noticed from the schedule of papers that more than 25% of the 25 papers are going to be presented that focus on hydrogen in iron and steel making. So the first area that I'm going to cover is the use of hydrogen in the production of direct reduced iron, where the complete replacement of natural gas for this process with hydrogen results in the production of only water vapor. The sponge iron or DRI produced can then be melted in an electric arc furnace as part of a low carbon integrated steel production process. And I will talk more about this in a later slide. And the use case of producing DRI with hydrogen, it has now been proven at a pilot scale and is being introduced at a commercial scale, as you can see from these projects, that are taking place currently in Europe, where very shortly the commercial scale operations will be starting. Hydrogen can also be injected into blast furnaces. However, there is a practical limit to how much hydrogen can be used because excessive hydrogen use cools the furnace due to the endothermic reaction that takes place and the high heat capacity of the water vapor that is formed. And this could destabilize the furnace's operation. So a hydrogen injection might reduce by 20 to 30% the carbon dioxide emissions for a blast furnace, but it will not achieve zero carbon iron on its own. And this slide shows some examples of where industrial trials have taken place with hydrogen injection into blast furnaces. Hydrogen, as I mentioned, can also be used to create thermal energy, and it can be used in reheating furnaces that typically run on natural gas. Hydrogen can be directly substituted for natural gas in these furnaces, as they both have similar combustion characteristics. Moreover, if a blend of up to 20% hydrogen is used, then the existing burners in the furnace can be retained. However, once you go beyond that and up to 100% hydrogen, new burners are needed because of the way in which hydrogen burns faster and hotter than natural gas. And here are a couple of examples of where hydrogen can be used in reheating furnaces. And just to clarify, I'm not spending time on these examples, partly because of the limits of the time today, but also if you to get hold of the presentation from me, you can see the references that you can then follow up with the websites for these projects. Surprisingly, hydrogen can also be used in electric arc furnaces, and this is because many EAFs use natural gas as a supplemental source of thermal energy to help heat the scrap metal and speed up melting. And simulation modeling has shown that using hydrogen instead of natural gas could reduce the carbon dioxide emissions from an EAF's off gas by up to 10%. And this is an example of where the use of hydrogen in an EAF is currently being researched. And finally, there are other use cases for hydrogen, and this includes using hydrogen in heat treatment furnaces for galvanizing lines, annealing, and in the hot blast stoves that preheat air for blast furnaces. Also mixing blast furnace off gas or natural gas heaters with hydrogen. And hydrogen can be blended with natural gas in combined cycle turbines that produce electricity and steam. And these are a couple of examples of these use cases as well. So bringing these individual hydrogen use cases together into an integrated decarbonized iron and steelmaking process really suggests the following preferred pathway. Firstly, producing DRI with hydrogen as the reactant, then potentially using hydrogen in an EAF as a supplementary source of thermal energy, and then using hydrogen for thermal energy in rolling mill furnaces. And by following this pathway, there is the potential to reduce greenhouse gas emissions from the iron and steelmaking process by 90 to 95% compared to current conventional technologies. However, the challenges of adopting this approach are twofold. Firstly, you have got a large capital investment that will be required. And secondly, there is the need to access sufficient quantities of low carbon, low cost hydrogen. However, this pathway really represents the only scalable end state pathway to truly near zero carbon primary steel. And while hydrogen-based DRI and hydrogen-fired furnaces are both being demonstrated and EAFs are well established, there isn't yet an operating facility that has that full pathway at an industrial scale. But the first such integrated plants, like the Hybrid plant and the Stegra plant, they are expected to come online in the very near future. So in summary for this section, hydrogen DRI enables near zero carbon iron making. Hydrogen injection into blast furnaces is really only likely to be an incremental abatement measure. Hydrogen use in EAFs is feasible, but it doesn't give a huge change in emission reductions. But it is that system level integration of hydrogen DRI, EAF, and hydrogen furnaces that will deliver the deepest emission reductions. So now that we've identified where hydrogen can be used within the processes of iron and steel making, we can begin to answer the question, well, where is the low carbon hydrogen going to come from? And by that, we mean two things. What technologies are available to produce the low carbon hydrogen? And secondly, how do these technologies compare to each other across criteria such as greenhouse gas emissions, capital costs, and production costs? And in this table, I've identified the main pathways that are currently available to produce hydrogen using a commonly referenced color coding system. And so firstly, gray hydrogen is the most common way today in which hydrogen is produced. And this uses a technology called steam methane reforming, which splits natural gas, CH4, into hydrogen and carbon dioxide using high temperature steam. And this process can produce hydrogen at a price of about $1 to $2 per kilogram. But the downside is that for every kilogram of hydrogen produced, on average, 7 kilograms of carbon dioxide are produced and released into the atmosphere. So this is not really an acceptable process for decarbonizing iron and steel making. A potential solution to this is to capture the carbon dioxide and to then store it permanently in an underground vault. And this is called blue hydrogen. However, there are downsides to this process, which are, the carbon capture process is not 100% effective, and it requires complex equipment that needs to be installed, powered, and maintained. And there are also CapEx and OpEx costs involved in transporting the carbon dioxide to a storage site, which might not be close to the facility. And there are also risks that relate to whether the carbon dioxide might leak into the atmosphere at some point in the future. So a more certain way to produce low carbon emission hydrogen is to use electricity to split water into hydrogen and oxygen using an electrolyzer. There are also some downsides to this process. Electrolyzers are expensive pieces of equipment and require fairly complex balance of plant to support them. And then the electricity itself needs to be produced from renewable or low carbon generation sources. And if necessary, the cost of building or accessing these sources needs to be factored into the hydrogen production cost. The final pathway here is an emerging technology called methane pyrolysis, which also uses methane as a feedstock and also exposes it to high temperature. But in this case, it is in an enclosed reactor, often in the presence of catalysts. And because the reactor is sealed and does not contain oxygen, the carbon atoms that are released from the CH4 molecule solidify as solid carbon, and no carbon dioxide is released into the atmosphere. And this means that the greenhouse gas emissions from this process are zero, but at a systems perspective, are limited to the fugitive methane emissions from the production and transportation processes. So if one of the objectives here in using hydrogen is around the reduction of greenhouse gas emissions, then this chart compares the four methodologies mentioned in the last slide. If renewable electricity is used to power an electrolyzer, then this is the superior pathway because it has zero greenhouse gas emissions. However, if electricity is sourced from a grid where the power is generated using hydrocarbon sources, then that will not be the case. And the red bar on the right shows the average greenhouse gas emissions of an electrolyzer process using electricity from the US grid. So in summary of this part, there are four possible hydrogen production pathways, each with distinct trade-offs. There's green hydrogen, which is cheap, but directly undermines the objective of decarbonization. There's blue hydrogen, which only partly cuts emissions and requires long-term carbon dioxide storage. There's green hydrogen, which provides a solution of truly zero carbon hydrogen, but comes with high costs and the need for renewable energy investment. And there is turquoise hydrogen, which is a promising new pathway offering low carbon hydrogen with potentially a lower energy cost than green hydrogen. And because methane pyrolysis is an emerging technology that some of you might not be familiar with, I want to just explore it in a bit more detail. But before I do, I want to draw your attention to this photograph, which is of a methane pyrolysis production system built by a company called Hycamate in Finland. And I'm showing this to you so you can get an idea of the componentry involved, which is mainly off-the-shelf industrial process equipment. So as I mentioned in the previous part, methane pyrolysis involves the thermal decomposition of methane into hydrogen and solid carbon. And this takes place in a reactor that is heated to temperatures ranging from 800 to 1600 degrees centigrade. And various heat sources can be used to achieve the necessary temperatures, including plasma torches, microwave radiation, and electric heaters. And also some of the hydrogen output can be combusted to supplement these sources of thermal energy. And the solid carbon that I mentioned can take various forms, such as carbon black powder, carbon spheres, or graphitic carbon, or other morphologies, depending on the reactor temperature and the catalysts that are used. So why would methane pyrolysis be a viable potential solution for producing hydrogen for use in iron and steel making? Well, firstly, as I mentioned before, the hydrogen can be produced with near zero direct carbon dioxide emissions. Secondly, it has a better energy efficiency and lower water use than steam methane reforming and electrolysis. And thirdly, the solid carbon co-product does have economic value. Carbon black, which is the most basic carbon output of methane pyrolysis, currently has a market price of about $1,000 per ton. However, with further processing, the carbon can be turned into graphene, which can be used in EV batteries, or even, or even into carbon nanotubes, which is a structural material. In these use cases, the market price can be up to $75,000 per ton for graphene and $300,000 per ton or more for carbon nanotubes. Although obviously in both cases, there will be the need for additional processing costs to take into account. Other benefits of methane pyrolysis is that the process does not require captured carbon dioxide to be transported or stored. There is flexibility in where the system can be located in a plant, because it just needs to sit close to a supply of natural gas. Also, the system can be designed in package sizes that enable a modular incremental implementation strategy to be adopted. And also, interestingly, the carbon co-product can also be used within the steel making process. However, there are some challenges in adopting methane pyrolysis for hydrogen production. Firstly, for every 1 kilogram of hydrogen that is produced from the process, 3 kilograms of carbon are produced. And this means that that large-scale carbon off-takers will be needed when the system size scales up. And this also will involve handling and transportation costs. And secondly, the process does consume more methane than steam methane reforming. So this increases its operational cost in comparison to steam methane reforming. And also it will increase the calculation of upstream fugitive methane emissions. And thirdly, as I mentioned, methane pyrolysis is emerging technology that's currently at the point of technological and commercial readiness, where the system vendors are generally small-scale businesses that are transitioning from operating demonstration systems to large-scale commercial systems. And having said that, there are quite a number of those vendors, and I'm pretty confident that within the next couple of years, many of them will have systems that are available for large-scale industrial applications. So in summary of this part, methane pyrolysis can produce hydrogen from natural gas without direct carbon dioxide emissions. Its co-product is solid carbon, which has an associated revenue stream. It can be easily integrated into iron and steelmaking plants that currently use natural gas for heating and reactants. It can be implemented in incremental modules, and the technology is proven, and vendors are moving towards implementing industrial scale systems. So all of this is great, but it doesn't mean much if the economics don't work in its favor as well. It is difficult to talk generically about the economics of using hydrogen in iron and steel making, because so much of it depends on particular factors such as type of production, process equipment, plant location, size, age, access to and cost of renewable energy, access to carbon dioxide storage, and many other criteria. However, I'm going to cover some of the significant points that drive capital and operating costs when implementing hydrogen production and utilization systems. Firstly, there are two primary cost levers that we need to consider in any investment decision to use hydrogen in iron and steel making. And the first is the cost of the low carbon hydrogen delivered to the plant where it's going to be used. And second is the capital cost required to convert existing iron and steel making routes to hydrogen enabled pathways and the operating costs of those pathways. So to compare the different hydrogen production pathways in terms of cost, the principle of levelized cost of hydrogen is commonly used. And this calculates how much it costs to produce 1 kilogram of hydrogen, including the cost of the feedstock, natural gas, electricity, water, the capital cost of the production and ancillary equipment, the overhead costs of running the production plant, and also any secondary revenue that is generated, for example, from the sale of solid carbon if the methane pyrolysis pathway is used. So in this chart, I've calculated the levelized cost of hydrogen for each of the different production technologies using ranges for feedstock prices, capital equipment costs, and infrastructure costs. And I've also provided an assessment of the LCOH of methane pyrolysis, where selling all of the solid carbon generates a revenue stream of $1,000 per ton of solid carbon. And what you can see is that producing hydrogen through the electrolysis pathway is considerably more expensive than steam methane reforming with carbon capture and storage, and therefore requires subsidies to be competitive. Methane pyrolysis, on the other hand, can produce hydrogen at a much more competitive price and has the potential, if the solid carbon can be sold on a long-term offtake agreement, to actually produce hydrogen at a negative cost. What this means is that I believe that methane pyrolysis can potentially play a pivotal role in overcoming the economic barriers to low carbon steelmaking by supplying lower cost, low emission hydrogen without requiring large renewable energy build out or carbon capture infrastructure associated with green and blue hydrogen. And its ability to generate valuable solid carbon byproducts creates additional revenue stream that can reduce the net hydrogen cost. Moreover, methane pyrolysis leverages existing natural gas resources and supports near-term adoption in regions where green hydrogen is not currently affordable. And collectively, these factors potentially make methane pyrolysis a powerful transitional and long-term solution for accelerating the cost shift to low-carbon steel. The other cost driver that I mentioned that we need to consider relates to the cost of converting iron and steel systems so that they use hydrogen. For example, transitioning to hydrogen DRI paired with electric arc furnaces, it represents a major capital investment requiring new shaft furnaces, electrical upgrades, hydrogen supply infrastructure, and supporting balance of plant equipment. And for example, a 1 million ton per year hydrogen DRI plant may cost $1 billion or more US dollars. And bringing together those two perspectives on cost means that inevitably the production cost of low carbon steel is going to be more expensive than the cost of steel using conventional production technologies. And without subsidies, this cost difference can be up to 50%. And this is the green premium challenge that the steel sector is currently facing. However, we should not forget two things. One, firstly, subsidies, tax credits, and carbon taxes can help level the playing field. And secondly, for some businesses, such as the auto makers and appliance manufacturing, actually the additional cost of green steel results only in a minimal increase in the price of their end product. And furthermore, this current cost premium for green steel is expected to decline in the coming years. And at some point, maybe in the next 10 to 15 years, I think the green steel premium is very likely to disappear. So in summary, hydrogen production costs and conversion capex are really the decisive economic drivers of using hydrogen to decarbonize iron and steel making. And these costs vary strongly by site and hydrogen production pathway. At the moment, low carbon hydrogen is more expensive than conventional hydrogen, but I think methane pyrolysis potentially does offer a lower cost, lower emission route to produce hydrogen by monetizing solid carbon and avoiding carbon dioxide storage infrastructure. And in addition, I believe that the green steel premium is likely to be only temporary. And as hydrogen costs fall, towards say $2 per kilogram, low carbon steel approaches cost parity with conventional production. So to conclude this part of the webinar, I would like just to give you three takeaway points. Firstly, hydrogen in iron and steel making really only works if the hydrogen is produced via low emission pathways. Basically dirty hydrogen solves nothing. Hydrogen DRI plus hydrogen in an EAF plus hydrogen in a reheat furnace pathway is capable of 90% or more emissions reductions. And economics, not chemistry, is the key constraint. Is the key constraint. Hydrogen cost and conversion capex drive the green steel premium. And finally, methane pyrolysis could materially improve the levelized cost of hydrogen by avoiding the need to invest in carbon dioxide transport, storage infrastructure, and by monetizing the solid carbon. And these are the references, and these are my contact details, which will come up on the screen later. So thank you very much, and Mike.
Well, thank you very much, Ian, and for a great presentation. Now I'm going to introduce Megan. She's speaking on the impact of ancillary equipment using hydrogen in iron and steel making. And thank you, Ian, and look forward to you speaking on, Megan.
Thank you, guys. Just flipping open my screen here. Okay, let me know that you guys can see the screen.
Yes.
Perfect, thank you. Okay, thank you so much, Mike, for the introduction, and thank you very much to Ian. That was a great presentation. So jumping in today, I'm going to focus on the impacts on ancillary equipment of using hydrogen in iron and steel making. So today, the four main things I want to touch on include hydrogen embrittlement, burner and combustion systems, compression and storage, and safety and ventilation systems. So just a quick introduction here. Using hydrogen in iron and steel making changes moisture loads, material behavior, combustion, and off-gas chemistry across a plant. Ancillary systems designed for natural gas now face new stresses and failure modes. Understanding these impacts is critical for safe, reliable, and efficient operation. So my presentation today is going to highlight the key issues hydrogen introduces for ancillary equipment, and it will also outline the practical mitigation strategies to adapt systems for hydrogen use. Okay, perfect. Jumping into hydrogen embrittlement, the things I want to touch on include metal degradation, seal integrity, and hydrogen quality. So hydrogen diffuses into susceptible metals, reducing ductility and promoting cracking and accelerated fatigue in high strength and low alloy components. Hydrogen readily permeates and degrades conventional elastomers, increasing leakage risks and requiring hydrogen-compatible sealing materials. Impurities and moisture significantly increase corrosion and cracking susceptibility, making hydrogen purity and dryness critical for long-term system reliability. So the image that I have here on the left, you can see that this is hydrogen embrittlement. So in our first image here, would be the hydrogen molecules. And then in the second image, this would be your low alloy carbon steel. In image 3, you see the absorption. So this is where hydrogen molecules dissociate into atomic hydrogen at the steel surface and diffuse into the metal lattice. In image 4 here, you see the accumulation. So the hydrogen migrates to microstructural defects such as grain boundaries, where it accumulates and weakens the atomic bonding. And then in image 5 here, this is under tensile stress. So these weakened regions initiate cracks that propagate rapidly, causing brittle fracture at stresses below the steel's yield strength. Okay. And then if we want to take a look at the mitigations associated with these, for metal degradation, you want to select hydrogen-resistant alloys, avoiding high-strength steels where possible, and controlling pressure cycling and ramp race. With your seal integrity, you want to specify hydrogen-rated valves, regulators, sensors, and compatible sealing material, such as PTFE. For your hydrogen quality, it's really important that you condition the gas stream to ensure dry, clean hydrogen with controlled impurity and moisture levels. So on a project I was actually working on, we needed to specify ethylene propylene for the seal material on all of our check valves, as these seals had the lowest temperature rating at negative 50 degrees Fahrenheit or negative 45 degrees Celsius. And due to hydrogen's properties, we needed to be prepared for the lines icing up or being extremely cold with large amounts of hydrogen ripping through our lines. Okay, next, if we want to take a look at the burner and combustion systems, hydrogen has a higher flame speed and elevated adiabatic temperatures, which increases flashback risks and changes your burner stability requirements. Hydrogen also has a lower radiant heat fraction and a buoyancy-driven heat flux distribution, so impacting refractory behavior and furnace modeling assumptions. As NOx and even CO formation are dependent on combustion temperature, higher hydrogen concentrations would increase due to the higher flame temperature. And you can see this as an example on the graph that I have here on the right-hand side of the screen. And finally, hydrogen has higher gas velocities and increased moisture loads, accelerating burner tip wear and contributing to corrosion in regenerators and recuperators. So the image that I have here at the top, this is a gas turbine fuel nozzle that was actually damaged from a flame holding event. So operating on a fuel with increased levels of hydrogen could also impact combustion system operability, including combustion dynamics. Pairing the correct combustion system for the target hydrogen percentage is critical to ensure reliable gas turbine operation. Next, if we want to look at the mitigations here. So with hydrogen, you want to mitigate instability and flashback by implementing hydrogen dedicated burners, flashback arresters, and recalibrating turndown and staging strategies. You would want to also recompute radiative and convective heat transfer profiles and adjust burner staging, set points, and soak strategies to reflect hydrogen's altered flame characteristics. For your emissions behavior, you would want to look at the control thermal, you would want to control thermal NOx through a combination of combustion strategies and post-combustion and after treatment systems, such as SCR. And then you would want to, of course, specify hydrogen-compatible burner materials, manage gas velocities, and evaluate regenerator and recuperator designs to accommodate the altered combustion chemistry. Okay, if we want to take a look at compression and storage, my first 2 points here are focusing on compression, and then the bottom, I will focus on storage. So first with our compression thermodynamics, hydrogen's low density and high specific heat ratio result in higher temperature rises during compression, increasing compressor discharge temperatures and thermal stresses. With your moisture and pressure control, condensation, seal permeation, and moisture accumulation increase the risks of corrosion, leakage, PRV instability, and water hammer in interstage systems. Now, if we want to take a look into storage, first, if we focus on the pressurized vessels, the higher the compressed gas, the higher the energy state the hydrogen is held in, which is typically an advantage. However, higher pressure gas always comes with risks. Higher pressure also leads to an increase in wall reinforcements to support the pressure. And with the increase in wall thickness, the vessel becomes heavier with a smaller volume, requiring more vessels and in turn more infrastructure. Working with increased pressure is tricky because you need to consider your stranded mass. Stranded mass is the hydrogen mass that will remain in your vessel once your tanks are quote unquote empty. So let me explain. When you open your storage, the gas will push out into the lower pressure. And once that pressure hits equilibrium, it won't be able to push any more gas out. So the remaining gas in your vessel is known as your stranded mass. Now moving on to liquid hydrogen. So as Ian had mentioned, gaseous hydrogen can be liquefied by cooling it to below -423 degrees Fahrenheit. So it takes a lot of energy to liquefy hydrogen, and using today's technology, this actually consumes more than 30% of the energy content from the hydrogen, and therefore it is extremely energy intensive. In addition, some amount of the stored hydrogen will be lost due to evaporation or boil off. This is especially true when using small tanks with large surface to volume ratios. In order for liquid hydrogen to reach the same conditions as compressed hydrogen, it needs to vaporize first through a phase change. This requires a huge energy shift. Additionally, if you have a tank sitting in the sun, it is incredibly hard to keep the hydrogen cold, and it would actually have a cloud of hydrogen gas inside at the top of the tank. And if the pressure were to build up enough in the tank, it would set off the PSV, and from this, you could lose a ton of your hydrogen product. Taking a quick peek at the mitigations here, with your compression, you could use hydrogen suitable compressors with enhanced cooling and strict inlet dew point control. You could also implement condensate management, continuous dew point monitoring, and a hydrogen rated seals and PRVs. With your storage, you could look at specified hydrogen certified vessels and validate pressure/temperature transients through thermal and CFD modeling. And with your liquid hydrogen, you could optimize insulation and boil-off management while confirming PSV and vent system design for heat in lake scenarios. So moving into our safety and ventilation systems. So the things we want to look out for here are, again, some of the things that Ian had already previously mentioned, where with rapid ignition and invisible flames, unique leak and dispersion behavior, and fast escalation. So hydrogen's extremely low ignition energy and non-visible flame increase the risk of undetected fires and rapid ignition events. Hydrogen's high diffusivity and buoyant upwards plumes cause hydrogen to accumulate quickly at elevation, altering traditional leak detection assumptions. And hydrogen's rapid leak evolution combined with enclosure geometry can accelerate hazard accumulation and increase consequence severity. And on the screen right now, I have two different codes and standards that show different hydrogen acceptable vent stack formation. So in my image on the left here, you can see this is from CGA G-5.5. Some people may be familiar with this. So this is typically what is used in North America, where on the photo here that I have on the right, this is actually from the European Process Safety Center. So a project that I was working on out of Australia, when we were designing our hydrogen vent stack, the team decided to go forward with the design configuration recommended from the EPSC. And the design is accepted under the CGA standards, but it is not a specific example that they provide in their text. The CGA accepts multiple configurations, and our client for this project requested a hybrid design that was being used in the time in several European installations. The vent stack has an improved design configuration against water ingress due to specific weather conditions that we were facing at site. And it actually facilitates an upward momentum to reduce detonation / deflagration potential, and it was a simple construction. Our mitigations here for your rapid ignition, you would want to implement a UV/IR flame detection, so hydrogen rated gas detectors and revised burner interlocks and AIST logic. For the unique leak and dispersion behavior, you would want to install detectors at high elevations and optimize ventilation through roof exhaust capacity, makeup air balance, and space partitioning. And for the fast escalation, you would want to conduct a fire and gas consequence modeling to validate detector placement, ventilation effectiveness, and emergency response design. So now I want to just touch on fire and gas consequence modeling quickly. Okay, so this is the typical 5 steps that you would have in fire and gas consequence modeling. So first, you would need to identify process safety hazards that would need to be screened. And then these hazards from step 1 are then reviewed to develop specific consequence scenarios to be evaluated. So for example, a hydrogen loss of containment. The selected scenarios then need to be analyzed to determine the potential consequences and potential impacts on occupied buildings. And if the initial analysis shows exposure to be high and that the mitigation is not practical, a more detailed analysis may be recommended to refine the understanding of the risk in a quantitative risk assessment or a QRA. So this is where a full probabilistic risk analysis would be performed to quantify the overall risk through a likelihood and consequence. Okay, and so the 3 main takeaways that I want to leave you with today are that hydrogen's higher flame speed and temperatures increase permeation, pressure dynamics, and embrittlement risks, cascade through auxiliary systems, and alter traditional design assumptions. These challenges can be effectively managed through informed material selection, combustion control strategies, moisture management, and consequence modeling. Hydrogen will have its place as a decarbonization tool, but its integration requires system-level engineering expertise to ensure the success of a project. Thank you very much.
Thank you, Megan. That's an excellent presentation. It goes into the great detail that we've gone into as understanding of handling hydrogen has increased in the last few years. We have a few minutes for questions, and we'd like to take the first one is from Brian Bliss for Ian Sutherland. Ian, you mentioned that carbon is an off-take product. What form does that take physically?
Yeah, great question. It can form a range of different products, depending on a number of criteria relating to the actual steam methane. The methane reform pyrolysis process itself, which are temperature and catalysts and the reactor design. At its most basic, you get a product which is called carbon black, which is a fine powder, and that's the most simple morphology that can be produced from a methane pyrolysis process. But you can get more complex morphologies that relate to a more graphitic type of carbon. So you get like solid carbon spheres that come out of it as well. I would just like to add that with all of these carbon co-products, there will be some element of post-processing that would need to take place depending on the actual usage of the product. Because you're producing something that's gone through, say, contact with catalysts, and so there can be some, metallic contamination that happens to it. And then if you do want more complex types of carbons, such as graphene or nanotubes, then that will require more sophisticated post-processing. Hope that answers the question.
Yeah, I think. Okay, well, thank you, Ian. The next question is from Renard. Can you explain, Ian, the faster kinetics of hydrogen reduction of porous iron ore? Of course, we all know that the smaller hydrogen molecule diffuses faster inside the pellet, but the larger water molecule must come back out again. So could you have a further explanation on that?
Yeah, look, I would probably prefer to follow up with an answer to that, because my area of expertise largely relates to the hydrogen production technologies, and the detail of that question. I wouldn't like to just sort of respond to it here. So if you don't mind, I can definitely follow up with an answer to that question.
Okay, thank you very much, Ian. Madison, we're at our closing mark. Would you like to finish us off?
Yeah, absolutely. Here's the results of the poll for everybody to review. General consensus is that the cost of low carbon hydrogen is currently too high. So curious to see if anybody changed their minds after hearing the presentations today. But I just want to thank you all so much for joining us. Ian and Megan put a ton of work into their presentations. Thank you both so much for taking the time to share your expertise with the group. And thank you to David and Mike for being our moderators for today. I'd also like to thank Big River Steel again for being our sponsor for today's webinar. And I just want to remind everybody that this webinar is recorded, and along with all of the other webinars that the Decarbonization Subcommittee has put together in the past, they're available on AIST's website. So that can be found under the Technology Committees tab or the Conferences and Expositions tab. We have some upcoming technology trainings that we we'll look forward to hopefully seeing you at, specifically to this group. We have energy reduction in the steel industry that'll be held in Cleveland this fall. And then we hope to see everybody at AIST Tech in May. So again, thank you so much. Really appreciate you all being here, and have a great rest of your day.
Thank you,
Thanks,
everyone.
buddy.
Thank you.